Hi everybody, today we're going to start learning about voltaic cells. If you've ever wondered what powers your cell phone or your laptop or your Prius, then this will be interesting to you. So in this section, after watching this video, you should be able to understand how a voltaic cell operates. And there's actually another name for voltaic cell, it's called a galvanic cell. You should be able to identify the half cells in which oxidation and reduction occur. So the one in which oxidation occurs is called the anode, and the one where reduction occurs is called the cathode, and we'll be talking more about that. And you should be able to identify the direction of the flow of the electrons. And finally, understand what a salt bridge is and what the spectator ions are doing and why both of those things are so darn important for a voltaic cell. Let's get started. So what is a voltaic cell? First, let's remind ourselves, we've been talking about redox reactions, and a redox reaction, of course, is an oxidation-reduction reaction. So something is losing electrons and something else is gaining electrons. So recall that if it's spontaneous, meaning it happens on its own under certain conditions, then electrons are moving and energy is being released. Well, in a voltaic cell, what we try to do is harness those electrons as they're moving around and get them to do useful things for us. So that energy of the electrons moving in a voltaic cell can do work. Now, we've talked about work before, and all the work we've talked about is pressure volume work, meaning we've got something pushing on something else, and that's doing work on it. So it's adding energy to that other thing. We also talked about if you lift a book up the stairs, you're doing work on the book because you are giving it more potential energy by raising it to a higher elevation. Potential energy is energy due to an object's position. Or we can talk about chemical potential energy, energy due to the bonds of the molecule that can be released. But we can also talk about electrical work. And basically, these electrons are starting out with high energy, like at the top of the stairs, although there's no stairs for electrons. And by the time they reach the other part of the voltaic cell, they're lower energy. So on the way, we've used that energy to accomplish something. For example, we could use it to light a light bulb. So if you think of an old-fashioned light bulb, it has a little filament inside of it. And so it has a high resistance. When the electrons are moving through that filament, it causes incandescence, which is light coming off. So we've taken some of the energy of those electrons and used it to do something. In this case, it was transferred to heat. And of course, that let off light. We could use those electrons' energy to, well, this is a flower, not a fan, but, well, I guess it's kind of a fan. No, it's a flower. Anyway, we could make it spin. That is doing work as well. And so let's figure out how this works. So we could call these things a voltaic cell. Here's a picture of a simple voltaic cell. So we have got, first of all, two electrodes. And they need to be metal, and they need to be different metals. And we'll talk about later on in this chapter why they need to be different metals. Not only do we need the solid metals, we also need some ions. So here we've got solid zinc, and the oxidation number of that zinc right now is 0. But in this solution, we have zinc 2+ ion, and you can see because we've got 1 molar zinc sulfate. Okay. Over here we've got copper as a solid, and its oxidation state is 0. But down here we've got copper 2+ ion because it's in copper 2 sulfate solution. Now, one of these is being oxidized and the other is being reduced. And we're not going to talk about which one's being oxidized and which one's being reduced quite yet, but you can see that one of these electrons are moving from the metal to the solution, and in the other direction is happening. So what's happening right now? As soon as we connect these wires, then we've completed a simple circuit. And in this case, it's just going through a simple voltmeter, which is telling me, hey, we've got a voltage there. A voltage is a potential. So it's basically saying, hey, we've got high energy electrons, and then by the time they complete this circuit, they are going to be lower energy electrons. So instead of hooking this up to a voltmeter, I could hook this up to a light bulb, and we would see the light bulb glow. Now, another really, really important part of this simple voltaic cell is this salt bridge, and it is a connection. Notice it doesn't allow the ions to get through. We've got to keep the copper ions and the zinc ions in their respective compartments, or we call those half cells. But what it does allow to get through are spectator ions, and in this case, the spectator ions are sulfate ions. We can see we had sulfate solutions of both of our zinc and our copper. And all of these things are going to be really important. If we didn't have the salt bridge, everything would stop immediately. If we ran out of either electrode, because one of the electrodes is going to get used up, the other electrode is actually going to increase in mass. If we ran out of either electrode, it's all going to stop immediately. If we disconnect a wire, it's all going to stop immediately. Because, if you'll remember, oxidation and reduction have to occur at the same time. We can't have oxidation without reduction. We can't have reduction without oxidation. So that's kind of an intro into how a voltaic cell works. Let's look a little bit closer. So here's a nice simplification of a voltaic cell. And I know what you're thinking, what? This is a simplification? It actually is. The first thing that you need to know is that oxidation occurs at the anode. Oxidation occurs at the anode. So in this case, zinc is our anode. Reduction occurs at the cathode. And the way you can remember this is an ox and a red cat. We wouldn't say an cat. So an ox, anode oxidation, and a red cat. All right, so oxidation anode, reduction cathode. And recall to yourself, oxidation is gaining or losing electrons. Oxidation is losing, and reduction is gaining electrons. Oil rig. Okay, so here we go. When electrons flow, the charges aren't balanced. So actually, let's first look at the flow of electrons here. Electrons always flow spontaneously from the anode to the cathode. So the electron flow is important. Because remember, the anode is oxidized. In this case, this electrode is just a general term for the piece of metal. It could be an anode or cathode. But this piece of metal is being oxidized. Therefore, it is losing electrons. And those electrons are going to the cathode. Now, don't worry about this cathode. It's called a standard hydrogen electrode. We're going to ignore that for right now. But right now, we know the cathode, red cat, is being reduced. So this is actually gaining, this piece of metal over here is actually gaining electrons. So once again, electrons always flow from the anode to the cathode. And we can see that we have a voltage here, a positive voltage. If the electrons were flowing the other way, we'd have the same value. It would just be a negative number. But electrons do not flow spontaneously this way. And the reason is it has to do with the activity series of metals. That will let you predict which way the electrons are going to go. We'll get there later. Now, here's a problem. As soon as this zinc loses its first electron, then it has become a little bit positive. And this has become a little bit negative down here. Now, have you ever seen a beaker of positive solution and a beaker of negative solution? And you have not, because we can't have charges like that that aren't balanced. And so the spectator ions are actually going to be what keeps things balanced in these half cells. So if we're moving negative charge over here, so negative charge is moving over here, how can we prevent that negative charge from building up in the beaker? Because think about it. If we have a bunch of negatives over here, then why would any more electrons want to go towards the negative? It doesn't make sense. And actually, if we started to build up a charge in either beaker, everything would just stop right away. But can you see anything that is moving along with the negatives? The spectator ions. So we can see for every negative that moves over here to the cathode half cell, we're also moving a cation that direction. So in this way, the charges stay balanced. Yes, we're adding negatives, but we're also adding positives. Now, let's look at it from the other perspective. As soon as this zinc anode lost an electron, remember, it would become a little bit positive, which is bad because then everything would stop. So what is counteracting that? There is an anion moving in the direction of the anode. And these spectator ions are so very, very important because without them, everything would stop immediately. So in a voltaic cell, we can't have any charges build up whatsoever. So anywho, to go back to this bullet point here, when the electrons are flowing, that would cause the charges to become imbalanced. And so we have this thing called a salt bridge. We have this thing called a salt bridge. Now, normally what you do is it could be even a piece of cotton, like a cotton rope or something like that, and you soak it in your solution. In this case, they chose sodium nitrate because they're small and permeable through this semi-permeable membrane. It can be like a cotton. There's different things that you can use for this. But anyway, the zinc ions can't get in or out through that salt bridge, but the smaller spectator ions can. So I know that this is pretty complicated so far, so let's just take a step back. Is that an oxidation half reaction or a reduction half reaction? That's our oxidation half reaction. So this zinc metal in this strip is giving up its electrons. Now, what happens to a zinc atom that lost its electrons? Is it going to stay with that piece of metal? And the answer is no, it can't stay with that piece of metal anymore. So as soon as that zinc atom loses its electrons, as soon as it becomes oxidized, it pops off and forms zinc 2+ ion. So that has moved into the solution. So can you take a moment and think what's going to happen to the mass of the anode over time? Given that the zinc is being oxidized, and once it's oxidized, it has to exist as an ion in solution, what's going to happen to the mass of the anode over time? And it's going to decrease over time. Because as long as that zinc is being oxidized and losing its electron and becoming an ion, there are going to be fewer and fewer of these zinc atoms over time. Let's take a look at what's going to happen to the cathode. This cathode is gaining electrons. And in general, the mass of a cathode is going to increase over time. This is a standard hydrogen electrode, which we'll be talking about later in this chapter. So this one's a little bit different, but hopefully so far you have a pretty good idea of what is happening inside of a voltaic cell. Let's practice this a little bit more. So in the cell, the electrons left the anode. This is an even simpler looking cell. So the electrons flowed out of the anode. We can get them to do some work, like light up a light bulb if we want. And they come out. We still have the electrons. This is important. We still have the electrons. They just are a little bit lower energy electrons than before. And they go to the cathode. And in the meantime, anions are migrating in the direction of the anode to keep the positive charges from building up in the anode compartment, and cations are migrating toward the cathode to keep the negative charges from building up. Have you ever wondered why a battery has two poles to it? A positive side where the electrons come out, and a negative side where the electrons come back in. So it's kind of strange. You would think that if we disconnected, so that part needs to stay connected, but you would think if we disconnected it over here, it should still continue to work. But we know that that's not the case. If this is disconnected over here, why does everything stop? The problem is we've prevented the electrons from reaching the anode. So reduction cannot occur without oxidation. So as soon as we disconnect either part of that battery, we have stopped the flow of electrons. So cations come from the anode department or compartment, and I know that that's kind of strange. And the hardest part about voltaic cells is just remembering where everything is. As the electrons reach the cathode, the cations are attracted to the cathode. So this was the one in the last picture that was just a little bit different. What's going to happen to the mass of the cathode? We said it's going to increase. So when this electron comes in, we can't have these electrons building up on this piece of metal. The metal would become negative. We've talked about that. Everything would stop. But what does happen is an ion in solution says, okay, now there are some electrons. In order for me to gain those electrons, I'm going to be attracted to this because they have opposite charges. And once that ion comes into contact with the electrons, it becomes an atom. And where does that atom stay? It stays on the metal. And so the mass of the cathode is going to increase over time. Hopefully that makes sense. So the cations gain the electrons and are therefore deposited as a metal onto the cathode. Do you think that this voltaic cell will eventually stop spontaneously moving electrons? And the answer is yes. A couple things could happen. We could run out of our anode, or we could run out of our ions in the cathode compartment, which can be attracted to the cathode. Or, as we've already said, we could disconnect anything, or we could remove the salt bridge. Any of those things is going to stop the flow of electrons. Can you think about how we would reverse the flow of electrons? Because remember, if it's spontaneous in the forward direction, then we know that it is non-spontaneous in the reverse direction. And this is how rechargeable batteries work. So we know that if we recharge the battery, we're using other high energy electrons from the electrical grid to make this non-spontaneous reverse reaction spontaneous again. So once we recharge it, what's going to happen to the mass of the cathode? Since we're going in the reverse direction, the cathode's mass is going to go back down. We're going to regenerate more of those copper 2+ ions. Now the electrons are going to the left, and so what's going to happen to the anode? It's going to regain some of its mass, and we are going to have fewer of the, I don't know what metal this is, maybe zinc. We're going to have fewer of those zinc ions. And so we've recharged our battery. By the way, the difference between a battery and a cell is just one of these things. A battery normally has many of these things. So I don't know if you know this. Inside of a battery, there's actually a bunch of cells that are next to each other. And inside each of those cells is a complicated chemical reaction, and there's salt bridges, and there's different metals, and there's all sorts of things. Okay, so that about sums this up. I know that this is pretty challenging, but it gets easier when you practice it. What I'd like you to do right now is consider these two half reactions occurring in a voltaic cell. So we've got a nickel electrode, and I deliberately did not tell you whether that was the anode or the cathode. And we've got a copper electrode, and you can see the half reactions there. So which one of the following descriptions most accurately describes what is occurring in the half cell containing the copper electrode and copper 2+ aqueous solution? So complete this sentence. What's going on in there? The electrode is blanking mass, and blank from the salt bridge are flowing into the half cell. By this point, I hope you can answer this question without looking at your notes. So do your best on that, and we'll see how you did. Go ahead and pause and give it a shot. All right, the correct answer was B. The copper electrode is gaining mass, and cations from the salt bridge are flowing into the half cell. If you'd like a little bit more practice on that, or you don't feel so sure about it, just take a look at sample exercise 20.4 in your textbook. So, after watching this video, you should now be able to understand how a voltaic or galvanic cell operates. You should be able to figure out the half cells where oxidation is occurring and reduction is occurring. We call those the anode and the cathode. You should be able to identify the spontaneous direction of the flow of electrons, and finally, know what the salt bridge is for and why it's so important to have spectator ions. And as a final question, I'm going to ask you, why do we need two half cells? Why can't we just have all of this going on in the same compartment? Why do we have to separate out the two half cells from each other? And as a hint, I'll remind you, what is the purpose of a voltaic cell? Why do we set these things up so that we can get something accomplished from that? All right, good luck.